Good morning. We were discussing about the electromagnetic fields, whether these electromagnetic fields which are caused by the transmission lines could be harmful for the human and also the animals. So, this is a interesting topic and a concern topic for the research as well as for the utilities. So, during 1990s most of the EMF, that is the electromagnetic field research, was focused on low frequency exposures, particularly from the conventional power sources from the power lines or generating from the electrical substations, or could be of the home appliances like the microovens, refrigerators, air conditioner units, so on. So, some of the studies have showed a possible link could be between the electromagnetic field strength and increased risk of childhood leukemia, but these findings indicated that such an association was very weak. So, there were no concrete proof that the magnetic fields generated by the appliances and the electrical power lines do support the theory of causing harmfulness to the human life. So, with the age of cellular technology, so several of the wireless routers being used in the cellular networks, likewise the portable GPS devices. So, the concerns regarding the possible connections between the electromagnetic fields and the adverse health effects still persist among the people, though current research continues to point to the same weak association. Some of the studies have been conducted on the humans show no evidence of any link between the electromagnetic field exposure and the cancer related or leukemia pertaining to the human disease like brain cancer, breast cancer, so on. Nevertheless, the international health standards recommend, and also the continued education on the practical ways of reducing the exposures particularly to the electromagnetic fields is very important, and people should be told about the importance, and also to see that minimum exposure to the electromagnetic field is necessary for the health issue. So, typically when you see the transmission towers, you have both the electric field and the magnetic field in the vicinity of the power transmission lines. Here are few of the examples for various voltage levels, 115, 230 and 500 kilovolts, where you see these are the towers, and the distance from the towers you can see that both the electric and magnetic field, electric field in kV per meter and magnetic field in milligauss, the values are very clearly given here. Say an example of a 500 kV transmission system, you can see the electric field, the kV 7 kV per meter being at the midpoint of the tower or very near to the conductor. As the distance increases from the tower, you can see the values of the electric field and the magnetic field getting reduced. Initially 7 kV per meter being the electric field and 86.7 milligauss being the magnetic field near the high voltage tower. So, it reduces as the distance decreases or you go farther away from the tower, say 91 meters, approximately around 300 feet, you see the electric field reducing to 0.1 meter and the magnetic field reducing to 1.4 milligauss. So, this is information for various electric and magnetic field pertaining to the transmission or higher transmission levels. So, the electric fields from the power lines are relatively stable because the voltage does not change. So, all the transmission lines which are operating at that particular voltage, say at 765 kV level, the voltage level fluctuation will be very less. So, the line because of the voltage level being maintained, the electric fields will be relatively stable, but the magnetic fields on the lines may fluctuate greatly, because this is due to the current changes in the response to the charging load. So, as the load which is being supplied by the transmission, which is being supplied to the load, when the loads change, the current magnitudes change drastically. Because of this, the magnetic fields which are there should be of concern and must be described statistically, because in terms of averages or the maximum or minimum values, which the fluctuation depends upon the load aspects. So, the magnetic fields above the mean normally calculated for various transmission lines, and it could be monitored and measurements could be done. So, various values for the different transmission systems are been given here. As mentioned earlier, the International Commission on Non-Ionizing Radiation Protection, which is an organization comprising of more than 15,000 scientists from more than 40 nations who specialize in radiation protection, have come to a common platform, and they have framed the guidelines pertaining to the electromagnetic fields exposure, where the severity of the magnetic field and the electric field near the people particularly who are working in the transmission or distribution or in the substation utilities should not be exposed with the specified values. So, here are some of the guidelines which have been framed by the association of ICNIRP. You can see here the exposure, say for 60 hertz power frequency supply, 60 or 50 hertz, in the country it is 50 hertz. So, in some of the countries they follow 60 hertz supply. So, the guidelines mention that is occupational, the people who are working in the utilities, say in the substations, or say people who are exposed for the transmission or the substation electric and magnetic field, who are working in the utilities or people who are involved in that, they should not be exposed more than 8.3 kV per meter in case of electric field, and in case of magnetic field the maximum exposure should not be more than 4.2 or 4200 milligauss. This is the value, and in case of general public, the values of electric field should not increase by 4.2 kilowatt per meter or 0.833 gauss or 833 milligauss. These are some of the guidelines which have been framed, and it is necessary to be adopted for the safe healthiness of the humans who are working in the utilities or in the transmission companies. So, electric field and both one gauss or 1 Tesla is equal to 10,000 gauss. This is one point to be noted. So, which is electromagnetic fields are measured in terms of gauss. So, 1 Tesla is equal to 10,000 gauss. So, the mitigation of the electric and magnetic fields is very, very important, and particularly concerning the transmission and distribution systems, could be overhead lines or substations. The proper mitigation techniques have to be employed so that a proper shielding factors or shielding has to be taken care, so that it could be reduced for the people who are working in the substation or in the transmission sector. So, various techniques are being employed for the EHV and UHV transmission and the substation aspects. So, one of the technique is to increase the height of the mast. Height of the mast is the tower mast where it is increased, and the clearances are more. So, with the clearances the electric field kV per meter comes down, and also the magnetic fields will get reduced on the people who are working on the earth ground level. Second being the conductor management, again we will be discussing about these aspects in detail. So, with the help of the proper conductor management, the mitigation could be done or reduced, electric field and magnetic fields could be reduced with the proper conductor management. And third being the compensation techniques. So, again various compensation techniques could be used to see how this could be reduced. The shielding factor is one of the important aspects to see that a proper shielding will help to reduce the fields. This graph shows you the effect of the mast, like increasing the mast, increasing the height of the mast. You see the reduction for various heights. You can see like when the conductor, you consider a tower with the conductor here, a 3 conductor bundle here. So, this height whatever the clearances from the ground, say this clearances from the ground, typically transmission system of 380 kilovolts is considered here with the current carrying capability of 1500 amps for the conductor, and the simulation of electric field is carried out for various heights, and you can see as the clearance increases the electric field reduces, that is the distance from the center is considered here. You can see for various height, that is 1 meter above the ground, the micro Tesla, that is the magnetic fields which are could be generated because of the 1500 carrying capability of the conductors. So, the height from 11.34 meters, that is a H is considered 11.34 meters to 12, 14 and up to 24 meters. You can very clearly see as the height decreases, the magnetic field increases. You can see the values typically for 11 meter clearance height with the conductor being charged at 1500 amps for a voltage level of 380 kV system, the magnetic field could be somewhere 23 to 24 micro Tesla. As the distance increases, the magnetic fields gets reduced. You can see for a 14 meter, 16, 20 so on. At a height of 24 meter, you can see the reduction from 23 micro Tesla to approximately around 6 to 7 micro Tesla. So, this shows that increasing the mass or the clearances could bring down the magnetic fields, particularly the magnetic fields near the ground surface on the near the tower, high voltage or extra high voltage tower, which are carrying more power. And also it should be noted that magnetic fields, as mentioned earlier, mainly depend on the current carrying capability of the conductor. So, the magnetic field will be more only when the current is very high. So, when the voltage is very high, current is less. So, magnetic fields are not of much concern, electric field is of concern. So, magnetic fields as the power transfer goes high and the current load is higher, then the magnetic fields the magnitude of the magnetic fields also go high. So, this is again a typical 765 kV transmission line tower configuration for vertical super bundle. You can see 2 circuits here, ABC and again here ABC, and you have 2 earth wires and lightning and the tower schematic here. This is the ground plane. Intentionally the earth wires are connected here, and you see the ABC and the phases are changed, and is a proper transpose is done to see that the advantages for transmission is better, and also reduction of the electric and magnetic fields to a certain extent in case of the conductor carrying more current. So, these are some of the things which some of the magnetic field and electric field values which have been simulated in the using developed software. So, for a 765 kV the curves have been shown both for the untransposed, this is for the untransposed normal tower 765, and this is for the transposed tower. You can see height above the ground versus the distance from the center of the tower. These are the equipotential plots which give an indication, and this gives the electrical field strength from the center of the cover. You can very clearly see here we have tried to plot both for untransposed and also the transposed. You can see the color red color which is been shown here is for the untransposed part, and this is for the ground is the transposed part. So, compared to the transport and untransport, the electric field strength reduces. This is one of the management of the conductors placement and going in for transposed conditions. Very important, one of the mitigation, very important mitigation technique which is being followed in the transmission system. Again, comparing for the ground field strengths, electric field strengths for different configuration, again for the 765 towers, you can see that for various towers we have carried out the simulations. These simulations results very clearly show that for the different towers and also for the transposition and untransposed conditions, that is a vertical super bundle type untransposed and vertical tower with transport system, and also for a flat tower and a delta type of configuration. So, 4 type of configuration studies have been done. Here you can see the electric field kV per meter versus the distance from the center of the tower. Very clearly you can see when the line is transposed, when the conductors are transposed, the voltage, the levels of electric field stress reduces. This is again in case of delta, the pink color shows for the vertical super bundle, whereas for untransposed you can see that the electric field strength is very high, near to 11 or 12 kV per meter. For the same tower with the transposition it comes down to 4. So, it reduces by 1/3 value. So, the very clear conclusion that the transposition going in for transposition will be the better option for reducing the electric fields. This is a similar study conducted for the tower configuration for a bipolar HVDC transmission lines for various voltage levels, 500 kV, 800 and 1000 kV lines from the data which is being obtained in the literature. For the tower details are been the data for the tower details have been obtained from the utility and also from the literature. You can this is again a schematic of the HVDC transmission tower. You can see the ground clearances where the conductors are connected. This is a bipolar line, DC line. This GW1 and GW2 are the ground wire connections 1 and 2 for a tower. This is a ground plane, and the distance between the two conductors will give the pole to pole spacing that as per the standards for 500, 800 and 1100 kV have been taken into consideration while estimating the electric fields. So, for the DC we have tried to estimate the electric fields for EHV and UHV DC lines. So, here you can see for a 500, 800 and 1100 kV estimations were carried out for a bipolar HVDC line. You can see the 500 kV HVDC line given in the red line shows, red curve shows approximately 11 kV per meter electric field. Similarly, for 800 kV it is 13 kV, and for 1100 kV system it is 12 kV per meter. Again, it depends on the height of the clearances which have been given and the tower pole to pole spacing and the ground clearance, very important. So, the values which were estimated have been compared with the actual dimensions of the available data from the literature, and the simulations have been carried out. So, for 500, 800 and 1000 kV you see the fields could lie anywhere between 11 to 13 kV per meter considering the distances. So, similarly comparison for the ground field strength for both ultra high voltage AC and DC transmission lines was estimated, and a comparison is made here. You can very clearly see the comparison conducted for both ultra high voltage AC and DC lines for the electric field strength. This y axis shows the electric field strength versus the distance from the center of the tower. So, for high voltage AC and DC, you can see the comparison. The red color gives the high voltage DC 500 kV line, which gives approximately the 11 kV per meter, which we have seen in the previous case. Again the 800 kV being the 13 kV per meter. For HVAC, you can see the fields are substantially less here, around 4 to 5 kV per meter, and in case of 1200 it is hardly around 6 kV per meter. These are done with the proper going in for the transposition of the conductors. Again this would reduce drastically. So, for comparing the 1100 kV HVDC and 1200 kV HVAC or 800 kV HVDC and 765 kV HVDC, you can see the electric fields will be definitely higher in case of HVDC, slightly higher, and for HVAC with the proper transposing the fields will be lesser. So, again a comparison of the ground magnetic strength for high voltage AC and HVDC. This gives the summary of the system details, that from 500 kV DC, 765 AC up to 1200 kV AC, both for AC and DC. For various towers, the flat type of towers, what was the maximum stress which was obtained kV per meter as shown here. In case of 500 it is summarized as 11.30, 765 kV it is 4.77, 1/3 reduction in comparison with the 800 kV DC lines. Similarly, for 1100 kV HVDC it is 12, and 1200 kV HVAC it is 6. So, almost 50% of the fields which have been or the maximum stress which have been seen in case of DC, comparatively lesser in case of AC. The second point, the one was the clearances, height, as mentioned earlier, the conductor management, very important. This we have also seen, that is the conductor management going in for the different configuration, and also the conductors being going in for a transposition. This will help in the reduction of fields, electric fields. So, here or magnetic fields. You can see a small example here, typical example of the design of vertical type of tower or a delta configuration type of, or how the conductors are managed and conductors are connected. This will be helpful. So, various options have been shown here. See example, this is one type of arrangement where the conductors have been connected, and this is the clearances. B is the vertical conductors placement, like as shown here. Third being the delta configuration in a rectangular equilateral triangle type, and the D being the inverted equilateral triangle. The placement of the conductors is being modified, and the studies have been carried out to see the fields behavior. You can see here for the magnetic fields, that is the micro Tesla per kilo amp. So, it depends on what is the current rating of the or the load which is being carried by these conductors. So, for various current rating in terms of kilo amp, the micro Tesla is been estimated, that is the magnetic field is estimated, and you see particularly of this configuration the magnetic fields are higher, and going in for either vertical or a delta or a inverted equilateral triangle type of arrangement of the conductors could lead to the better performance of the line, and also the magnetic fields getting reduced. So, this is how it is being shown here, and this gives the per unit versus the distance from the center of the values. So, further the conductor management, again there is one more option which is being done, like the phase splitting. So, phase splitting, a typical example is shown here for a 300 kV transmission line carrying a current of 1500 amps, and you can see for various configuration how the performance of the magnetic fields from the center is shown for various configuration A, B and C. You can see how the configuration is given here, so that this will improve the performance and gives a better information to the utility engineers who could plan to see how properly the conductor management could be made for reducing the magnetic fields or the electric fields particularly. This is one more method of going in for passive compensation. Here you can see that the distance from the center, again here the magnetic field reduction is seen with a loop, particularly for using a series capacitor of 12 microfarad. This is without loop, the magnetic field could be slightly higher. So, various types of mitigation techniques are being employed by the utilities. Further, shielding by metallic materials. So, that now materials play a very important role. So, either shielding of this magnetic fields could be made by using a magnetostatic shielding or using a flux shunting mechanism, where typically using a proper metallic materials where the magnetic flux which comes in the vicinity could be diverted because of using a proper shielding mechanism. So, either shielding by eddy currents or by induced current mechanism or going in for magnetostatic shielding will help in reducing the magnetic fields. Going in for a ferromagnetic or a pure magnetic shielding aspects, here again the various materials are available with a different relative permeability, that is the initial and high permeability, maximum permeability values are also specified. So, various materials like iron, steel, low carbon steel, ultra carbon, hot rolled, ultra low carbon silicon steel and param alloy, which is also known as micro material. Some of this magnetic shielding using these materials are also been tried out to reduce the fields. How to mitigate the fields, particularly for the underground cables? For the overhead conductors we have seen. For the underground cabling, again it depends on laying geometry in the cable, how it is laid, and what is the depth of the cable trench which is being adopted for the voltage and the dimension of the cable. So, here also introducing passive loops could help in reducing the magnetic fields, also allowing currents to flow in the metallic sheath on the cables. Then shielding by conductive metallic materials will again further help in reducing the magnetic fields of the underground cables, and shielding by the ferromagnetic metallic materials will also help to reduce the fields.